Okay, good morning, everybody. Let's get started. First of all, thanks for being flexible last week with me not being here. I dropped 2 recordings from last year that spanned everything we should have talked about last Thursday, but that I was in no state to do live. So hopefully that was okay. And hopefully you did tune in and followed along with the conclusion of Lecture 6 on physical simulation, which closed out that Lecture 6 finishes with physical simulation and shows how a roboticist needs to start coding or building additional components on top of a physics engine. A physics engine doesn't usually come out of the box with various sensors and other kinds of things, neurons and synapses, things you need for an autonomous machine. Those are the things you need to build on top of a physics engine, which undergrads you're now in the process of doing in assignments 4, 5, and 6. All good about physics engines? Any burning questions that came up while you were watching Lecture 6 that's worth revisiting, which I'm happy to do? No? Okay, then that closed out last week our theme on the tools of the trade, and I and my guys last year introduced you to the beginning of the history of evolutionary robotics. Evolutionary robotics is a new field, started in about 1992, so where are we now? About 33 years in. That's not a very old field. So we're not going to have that many lectures on the history of evolutionary robotics. We will very quickly get, by the end of Lecture 10, to a whole bunch of open questions, things that are still unresolved in evolutionary robotics and robotics in general. And in a moment, we will dive back in to Lecture 7, the first years and the first few experiments on evolutionary robotics. But before we do that, just a reminder and orientation about assignments. Undergrads, you are now working on assignment 5. Grad students, you are working on the penultimate and the ultimate assignment in the easy path, quote unquote, the easy path. So for the graduate students, when you finish assignment 9 and 10, you'll be done with the easy path. You will have an autonomous virtual machine running around inside a physics engine, and that physics engine will be wrapped in an evolutionary algorithm that you can tune via the fitness function to get it to evolve robots to do different things on your behalf. All good? Okay. Grad students, what that means is next Tuesday you will start in on assignment 1 of the hard path, where you're going to do everything again, but instead of wrapping the physics engine in an evolutionary algorithm, which, as we talked about a while back, an evolutionary algorithm is a random trial and error process. You're going to recapitulate or redo everything you just did in the easy path, but now instead of an evolutionary algorithm, you're going to use gradient descent, which is a different type of search method that is not random. There is no, there's trial, but there's no error. And we'll talk a little bit about that briefly for the grad students next week when they start in on that. And then we'll come back to gradient descent as it relates to robotics 5 weeks later when all of the undergraduates also get to that point. Okay. Everybody know where they are and where they're going? I don't hear anything otherwise, so I will assume yes. Okay. All right. So Lecture 7, the early years of evolutionary robotics. As I mentioned last time, just backing up a little bit. Sorry, not 1992, 1996. I misspoke. In 1996, around that time, there were 2 papers that were published in the scientific literature at about the same time. So there were 2 groups that sort of invented evolutionary algorithms. The first group is a bunch of researchers, Italian researchers working in Switzerland. So it's now become known as the Italian approach. And we'll talk about the English approach that was started about the same time on the other side of the English channel. Okay, so Mondada and his colleagues reported on evolving robots using a physical robot, and they used this particular physical robot, the Kepra. It's morphed over the years into this robot, which some of you might have at home, and anytime you order something on Amazon, it's usually picked up in a bin using one of these robots. These two-wheeled robots with a couple sensors on the front should also look familiar to you. Where have we seen that kind of hardware before? Anybody remember? The Bradenburg vehicle. So you can see this sort of common thread of thinking in robotics, starting with Bradenburg in the 90s, into Kepler, physical instantiations of those Bradenburg vehicles in the 90s, and up to today. This is a very common platform or a way of approaching robots that need to do relatively simple tasks. Clean the dirty floor, find something on behalf of you and Amazon, and so on. Okay, I think we got this far last time. So with the Kepler robot, how did these Italian researchers evolve these robots? They did all the evolution on a physical machine, no physics engines, because physics engines weren't invented yet. The computer games industry sort of invented and started distributing physics engines or physics-based games in 2000, so 4 years after this experiment was reported. So the researchers had the idea about why don't we take these things called genetic algorithms or evolutionary algorithms, which had been around since the 70s. That was an old idea. Why don't we take these evolutionary algorithms and get them to evolve brains for our robots, to get our robots to do whatever it is we want them to do. Tricky to do at the time, given the hardware limitations, so this is how they did it. They took the Kepler robot, and you can see there was a physical tether. There was an actual wire that connected the robot back to the computer. The computer is going to run the genetic algorithm, and the robot is going to do all of the behaving. Okay. The nice thing about the Kepler is because it's so small, you can do tabletop experiments. You don't need an enormous lab. They put a laser emitting device up in the corner of this box sitting on top of this desk. And the laser that was emitted swept over this space and was detected by the Kepler. Another nice thing about the Kepler is that it was modular. You can stack different things on top. Here's a little gripper that's holding a sugar cube. We'll come back to this sugar cube gripping robot in a few weeks. You can put a little gripper on top. You can put a little eye on top. You can also put something on top that detects various types of sensors. So in this case, the Kepler was picking up the laser, and based on the laser intensity, the little robot had enough circuitry on board that it can compute its position, its X and Y position on the top of the table, and its heading alpha. So at every time step, or about every 1/10 of a second, this robot, as it's moving around, knows its X and Y and alpha. We can feed that back into the evolutionary algorithm and evolve a little neural network for our robot, so that this robot takes as input information about its current state, and it outputs commands to the motors to turn the motors forward and back. And we've got a little robot that can do that on a table. What kinds of things might you evolve it to do, given all those bits of hardware and software?
Like follow a certain path or something.
Follow a certain path. So path following seems reasonable. Don't fall off the table. Obstacle avoidance. Those kinds of things, right? This is early days of robotics. Those are the kinds of tasks we're going to look at here and in the next few weeks. Okay. It was very close to path following. They got a couple of foam pieces and made a little racetrack for their robot. And they're going to try and evolve the weights of the neural network inside the robot so that it circles through the maze as fast as possible and doesn't hit the walls. Not too difficult. They did not, in this experiment, evolve the neural architecture inside the robot. Remember, neural architecture is the number of neurons, number of synapses, the connectivity, how the synapses are wired together. The researchers set or fixed the neural architecture. This is it. We'll talk about it in a moment. They just set the genetic algorithm or the evolutionary algorithm to evolve the weights for all of these 12 or so synapses inside the robot. And because we're dealing with a physical machine, the genetic algorithm also wasn't evolving the body of the robot. So very Cartesian at the moment. We've got a hardware body, we've got a brain for the robot, and the genetic algorithm is just going to evolve the weights for the brain of the robot. Okay, let's have a look at the neural architecture they came up with and why they came up with this architecture. We can see our two wheels here in black and the two motors here in white. And then we have 1, 2, 3, 4, 5, 6, 7, 8 proximity sensors. So this robot does not just know X, Y, and alpha. It also knows it's got 8 numbers coming in every 10th of a second that are reporting proximity. Anybody have a guess about how these proximity sensors were built? This is hardware, not physics engine.
It's like echolocation, kind of.
It's exactly echolocation. So all of these 8 sensors here send out an infrared pulse, a beam of light, a very short pulse of light, and that light goes out of the proximity sensor and hits something and scatters. Some of the light goes that way, some of the light goes that way, some of the light goes that way, and some of the light goes this way. It emits a short burst of light, so the sensor can detect the time interval between when the light pulse is emitted and when or if the light pulse is returned back. The further away the proximity sensor is from something, the longer it takes the light to get back. Yeah? So from the perspective of the neural network, this neural network is receiving at each time step 1, 2, 3, 4, 5, 6, 7, 8 numbers. Those numbers are an estimate of proximity. The longer the time interval, the shorter, or the closer, the higher the value, the closer something is to that sensor. Make sense? Okay. We're not drawing our neural network here in the usual way where we have an input layer and then a hidden layer and then an output layer. We're drawing the neural network embedded in the physical body of the robot. 6 sensor neurons in front, 2 sensor neurons in the back, 2 motor neurons in the center. The left motor neuron sends its value to the left motor, and the right motor neuron sends its value to the right motor. Not that different from the Bradenberg vehicle. We've just got a few more sensors and a few more synapses. You'll notice one more detail that the researchers built in. They labeled some of the synapses as excitatory connections, shown by the arrows, and some of the other synapses or connections. Connection and synapses here are synonymous terms. Inhibitory connections are shown with these sort of arrow fletches on the back here. Okay. You'll notice some of them are excitatory, some of them are inhibitory, and the researchers set this manually. Why? And why did they choose this particular pattern of excitation and inhibition? What is the pattern?
I'm not sure. Can you point out like 1 or 2 of the inhibitory connections?
Sorry, yes, it's a little difficult to see. So let's take this left hand proximity sensor. You'll notice it sends an excitatory connection to the left motor. And let's take this proximity sensor here and follow this sensor here. I'm sorry, it's hard to see in this picture. That's the symbol for the inhibitory connection. Might be hard to see in the back. There is a pattern. It's not arbitrary. What's the pattern?
Like the left side of the proximity sensors send excitatory connections to the left motor, and then like vice versa.
So the left sensors are sending excitatory connections to the left motor neuron, and the right sensors are sending excitatory synapses to the right motor neuron. Same sensor, same motor, same side, that's ipsilateral connections. So the ipsilateral connections were set to be excitatory. signals that go from the left side to the right motor or from the right sensors to the left motors. Actually, you can see a little bit better here. Let's follow this one. That's an inhibitory connection. The contra across sides, contralateral synapses are inhibitory. Why? Why did they choose that?
I believe it's because that means if an obstacle is closer to one side, it will turn away from that obstacle.
So they're building in a little bit of Bradenberg's coward vehicle, right? You'll notice that the widths of these lines are different. The widths represent the magnitude of the weight. A thick inhibitory connection means strong inhibition. A thick excitatory connection means strong excitatory connectivity. The magnitudes, the thicknesses of these lines, that's what the genetic algorithm discovered. So you're actually looking at an evolved solution here. The combination of the thicknesses of the lines, this is what the genetic algorithm discovered. The pattern of excitatory and inhibitory connectivity set by hand. So the researchers are kind of giving the genetic algorithm a strong hint. They're biasing solutions for the robot to turn away from obstacles, which in this environment is the walls of the race course. But just turning away from the walls is not sufficient to do this. It'll help with this, doesn't help with this. So this is a partnership between man and machine, the human researchers and the evolutionary algorithm. Everybody see that? Okay.
Would this be able to go backwards? If it received a strong enough inhibitory response, like if something was dead ahead of it, would it be able to back up or would it just stay still?
Good point. Thank you. Okay. You'll notice that the researchers are not going to ask the evolutionary algorithm to evolve robots that circle through the maze forward as fast as possible. Part of the reason why they went to all this effort is to see what kinds of solutions might the evolutionary algorithm come up with. And more interestingly, might it come up with solutions that we wouldn't think of, right? Hopefully, until you ask this question, most of you are assuming when I flip to the next slide, you're going to see a robot racing forward through the maze, because of course that's how you solve this problem. That's how humans tend to solve this problem. Why? It might seem ridiculous why we're even talking about this. Why does it seem so obvious to us that the solution, possibly the only solution, is to drive forward around and around the maze?
Well, we have like forward-facing eyes and our bodies kind of built to move down.
That's exactly it, right? Here's our sensory system. It points forward, so that's obviously the way things should be done. This robot, it's got more eyes in the front, but it also has eyes in the back of its head for exactly this reason. They wanted to explore this question, this engineering question of how do you evolve machines to do something on our behalf, but they're also asking a scientific question here. How else can we get machines to solve problems that are different from the way we might solve them? Okay, so there's a couple of ways this problem could be solved. Drive forward around and around the maze as quickly as you can. Drive in reverse as quickly as you can through the maze. That's it, right? There's only two solutions. Thinking about thinking is misleading.
It can do a combination of both.
Sure, why not, right? There's no reason why I can't do this. Not so comfortable for us, and don't try this in a vehicle, especially today. Not comfortable for us, right? There are clear biases in how we like problems to be solved. For most real-world problems, there are an infinite number of solutions, and we often don't think about it. And when we ask our machines to solve the problem, sometimes it comes up with the solutions that are the way that we like them to be solved, and sometimes they're not. Sometimes that's a horrendously hilarious or dangerous problem. Sometimes it's a good thing. Sometimes machines can solve problems better than we can because they find other solutions.
Yeah, there's one kind of difference I see here is we can keep moving forward, but we can like look left and right.
Yep.
Whereas the robot has to, well, I guess it sees everything.
It sees everything. I haven't really given you the details about these 8, but you can assume it's got more or less 360 vision without having to turn its head. It can't turn its head. It doesn't have a head. It can see 360. By the way, it can also drive in a spiral through the maze. It's a better driver than you or I will ever be. Yeah? Okay. I'm spending a lot of time on this point with this ridiculously simple robot and this ridiculously simple task. But again, a lot of what we're going to see in this course look like straightforward engineering problems. We're trying to build autonomous machines, but there are deeper philosophical questions under a lot of these experiments. Okay. All right, you've been very patient with me. Okay, so a couple more details. We've got our motor neurons. We're going to assume that the motor neurons have an activation function associated with them. Remember, an activation function squashes the values of neurons into some desired range. In this case, the desired range is between minus 0.5 and plus 0.5. The wheels can spin backwards, negative. The wheels cannot spin at all, 0. The wheels can spin forward, 0.5. And every velocity, every rotational velocity in between. Okay, let's assume the 8 proximity sensors return a value between 0 and 1. A value of 0 means from the perspective of the proximity sensor, there's no obstacle in front of it. 0, 0, 0.1, 0.2, 0.3, 0.4, 0.5, 1. I am in contact with something. There is no time interval between sending out an infrared pulse and getting the response back. Okay, those are the range of values that the 8 sensor neurons and the 2 motor neurons can receive. Let's now construct a fitness function for our genetic algorithm. Let's assume that we want this function to take on values between 0 and 1 and all values in between. And you can construct this fitness function from the following 10 Lego bricks, and you can use them multiple times. VLVR, the rotational velocity of the wheels, and the 8 values of the infrared sensors. I want you to think about that. While you're thinking about that, keep in mind that we're using these 10 values twice. These 10 values, or the 8 sensor values and the 2 motor neurons, they're being computed or used within the neural network. And then the genetic algorithm is also going to receive a copy of these 10 values and combine them into a fitness function. This can often be confusing when we start talking about sensor values and motor values. They're being computed within the neural network, but they might also be used by the evolutionary algorithm to compute the performance of the behavior of any given neural network operating inside the robot. So far, so good? Okay, have at it. Ideas. Not surprisingly, there's no one right answer here, and some fitness functions are better than others. The genetic algorithm is going to generate a set of 12 weights or so, drop them in the neural network. The physical robot is going to drive around in the maze for a few seconds, and then we're going to take all of those values, pull all those resulting values out, and compute the fitness function. Ideas. I've simplified things for you a little bit here. Let's assume that VLVR and the other 8 proximity values, they're averaged over the few seconds that the robot operated. I could have given you VL1, the left rotational velocity of the wheel at the first moment in time. VL2 would be the rotational velocity of the left wheel a tenth of a second later, and so on. Let's just assume these are 10 averages. Ideas?
Yes.
we could maximize for the speed of the wheels, the magnitude.
Okay, let's maximize, let's assume we drop in here that we, to the magnitude of the wheels, VL and VR, VL plus VR, the absolute values of VL, VR. Let's run that genetic algorithm in our head. What kind of solutions do you think you're going to get? What's the robot going to do? What's the robot going to evolve to do?
It's going to, if you don't give it anything else to fitness function, it's going to ignore the values of proximity sensors and just go as fast as possible.
Yes, the genetic algorithm is going to evolve the infrared values, and the robot is going to ignore the infrared or the proximity sensor values in the sense that it won't incorporate them into its behavior. They're being computed and they're propagating through the neural network, but they're not really affecting the motors. So the robot is going to probably do what?
Go in a line.
Go in a line. Obviously. If we sum them, yes. You mentioned if we take the absolute values. What happens if we take the absolute values of VL and VR? What possible behaviors are we going to get? Phi equals absolute value of VL plus the absolute value of VR. What kinds of behaviors would evolve? Could spin in place, could spin the other way. Both wheels could go backwards and it could crash backwards into the wall. As we look at lots of different fitness functions in this class, I want you to try and run the evolutionary algorithm in your head and try and guess what kind of behaviors are going to come out. Okay, so let's assume for the purposes of science here, we want to see what kind of behaviors we get. Let's assume we do throw into this fitness function the absolute value of VL plus VR. So we know the kinds of things we're going to get, but some of those solutions are go forward, crash into the wall, go backwards, crash into the wall. That's a necessary condition, but not sufficient. We got to incorporate the infrared sensors in there also so that it doesn't crash into the wall. How might we do that? We've got this so far. We want phi to be maximal. We want it to obtain a value of 1 when the robot is doing a really good job of what we want it to do, and a value of 0 when it's maximally misbehaving.
And then could you like subtract the weight of the proximity sensors? I don't know like how.
Let's try it. Okay, we're going to subtract, and I'm just going to sum up. I'm going to use sigma to just sum them all up. We've got 8 of them, so let's use n here. N equals 1 to 8. So we're going to subtract the sum of all the proximity values that the robot experienced while it was behaving. If we use this fitness function, what kind of behavior are we going to get?
If you're subtracting the sum of them all, then the farther it is from something, then the closer it'll be to 1, or the closer it'll be to 0.
Closer to be 0. So there's a lot of double, triple negatives here, which are tricky, right? So a proximity sensor that's facing something has a low time interval, which results in a high value. The closer the proximity sensor is to something, the more proximate it is to an obstacle, the higher the value. Up to 1 when it's actually in contact with the wall of the maze. I think you had it. Can you tell us again?
I don't know.
Not so sure?
Are we using the average of the proximity sensor?
We could take the average if you want. So this ranges between 0, each individual I ranges between 0 and 1. So if you want to take the average, we divide by 8, okay? Think about when this entire formula is lowest, what would the robot be doing? And think about when this equation would be as high as it could possibly be, what would the robot be doing? Remember that this is our fitness function, phi, and the fitness function is being maximized by the genetic algorithm. Yep?
I feel like the sort of optimal behavior would be for it to be sort of like equidistant from both the walls and then just spin.
Could be, right? So this could be spinning, this wheel could be spinning forward really fast, which gives a high value here. This could be spinning backwards really fast, which gives a high value because of the absolute. So we've got 2 high values here, and if it's staying away from the walls as best it can, these are as low as they're ever going to be. They may never be 0 inside this particular maze, but that's as low as they can go. So good observation. Whatever this thing is, it's not perfect. There are perverse instantiations of this fitness function. There are ways the evolutionary algorithm can get this whole thing to obtain a high value, possibly near 1, that doesn't lead to racing around the maze, the thing that we want. It's instantiated the fitness function. It's found a set of weights that makes this value very high, but does not produce the behavior we want. Yeah? Okay. Can we fix things? Driving fast forward around the maze is okay. Reversing through the maze and not hitting the walls is okay. Doing tight little spirals through the maze is okay. Tricky, huh? I mean, this is a pretty simple robot, pretty simple task. It's not easy to see how to write down a fitness function, which is kind of the point. This is one of the big challenges in robotics. Write a fitness function for autonomous vehicles so that they get you quickly and efficiently where you want to go without hitting anyone, obeying traffic laws, driving a little bit differently on different terrain. Not an easy thing to do. Ideas?
I guess if it needs to be just the speed of the wheels and the value of the proximity sensors, I'm not certain, but if you add something if you add something to the fitness function for its either position or time it takes, then maybe, because that will let you better emphasize that it should be moving around instead of just, because the issue with the last one was that the way we had it set up, it didn't care about actually going through the maze.
Exactly. So VL and VR tell the evolutionary algorithm how much or how little the wheels are moving, but not how much the robot is moving. We want the robot to displace. Don't stay in place. Go forward, go back. How do we do that? We could include additional Lego bricks. We could try and put additional sensors on the robot, give it more state. Turns out you don't have to.
If you add the 2 velocities together, then like when it's a positive value, it'll be going forward. When it's a negative.
This will reward for forward travel, right? This will maximize, the evolutionary algorithm will maximize forward travel. But we also want to allow it to go backwards if possible. How might we modify this so that going forward quickly or driving in reverse quickly is okay? Either solution is fine.
You just take the absolute value.
We got the first part of it. This is what you'll see in a moment, this is what the researchers built in. This is one term. So this term leads to fast forward travel or fast backwards travel. Okay, we got one half. Now we got to go back and fix the and don't crash into walls part. Remember that we want this to be high when the robot is going fast and not crashing into walls. And we want this to be low when the robot is not moving very much or crashing into walls. What goes in here?
You subtract the summation last time. What about adding summation?
Subtract the summation.
No, what about adding?
Adding it?
Subtracted it last time, now bring it closer to 0, but if you add it, it's a, wait. Actually, that's right.
This says go forward or go back and crash into walls as much as you can. Okay. So actually, this isn't bad because you found the exact opposite thing of what we wanted to do. How's that? Run the evolutionary algorithm in your mind. For this to be high, this has to be high, and this has to be as low as possible. Eyes are always, the proximity values are always positive, so the evolutionary algorithm is going to drive this term as close to 0 as it can. I think we've got it. Everybody see that? Okay. Turns out this is close to what the researchers did. This is close to what the researchers did. So we talked about this. This is okay but problematic. This allows go forward really fast, go backwards very fast, and turn in place. I don't know why the researchers didn't do this. This would have been simpler. But what they did is they took this term, which ranges between 0 and 1, and they multiplied it. They multiplied it by this term, and they took 1 minus the square root of this thing. It's a little complicated. So let's work from the inside out. Here we're taking the absolute difference between these values. We're then doing 1 minus this. So it's very much like our negative term over here. They're trying to drive this as low as possible. Minimize this. Minimize the difference between VL and VR. They put it through a square root first, which gives a strong weight to small differences. What does that mean? Okay. Let's plot on the horizontal axis delta V here. And then let's plot on the vertical axis here the square root of delta V. As delta V starts to increase, as the differences between VL and VR start to diverge, as the evolutionary algorithm is starting to evolve a robot that's turning and swerving through the maze, which is what we don't want, the square root, you may remember, has a curve that looks like this. So the further to the right this starts to be, the more badly behaving the robot is being. It's swerving back and forth, and so the hammer comes down. There's a strong penalty to this. If we didn't take the square root, we'd just have a straight line, and there'd be less of a penalty when things start to go wrong. The square root here, in essence, is trying to nip in the bud the evolution of pathological behavior, bad stuff. If you're evolving or training an autonomous vehicle and it's learning to accelerate and decelerate really quickly, there should be a penalty term that comes in very quickly and says, root out that problem before it evolves any further. Okay, so uppercase V rewards for high magnitude at the wheels. It's multiplied by the second term, which penalizes differences between the magnitudes of the wheels, which taken together gives us more or less something like this. But it's got a little twist in it. It's being a little more, it's punishing this a little bit more. And then they're multiplying this by 1 minus I, where I is the maximum among these 8 values. Instead of trying to get all the proximity sensors to be as low as possible, by taking the maximum one, the one that's firing the most strongly, here's one that's firing strongly, here's one that's firing weakly, we only care about the one that's closest to a wall. Question?
Wouldn't this penalize turning too, though?
Good point. Yeah. So these two taken together penalizes turning. Okay, so penalizes turning, so the robot tends to go straight, starts to evolve to go straight, and starts to get closer over evolutionary time to this wall, which causes what to happen in this term? This term, the I will approach, right, this term will approach 0, that's right. So the closer the robot gets to any wall, the higher I starts to climb. 1 minus the higher value means this whole term starts to approach 0. And we're multiplying these 3 terms together, so phi starts to approach 0. There's a tension here, isn't there? Some of these terms are pulling the evolutionary algorithm in different directions. This term is pulling towards spin the wheel. This one is penalizing differently spinning wheels. This one is penalizing getting close to walls. There's a tension here. There's always a tension in nature between different competing values. Yeah? In our species, evolution would like us or our bodies to get as much oxygen to every cell there is. And the best way to do that is when we're a single cell, don't divide. Stay as a single-celled organism. That's a really great way to make sure that all cells that make up the organism get enough oxygen. But there is also evolutionary pressure in our species to divide, and get bigger and bigger and bigger for various reasons. There's a tension between size and vascularization or oxidization, getting enough nutrients and getting big enough. There's tens or thousands or millions of other competing tensions going on in your body all the time from an evolutionary perspective. There is no optimal solution to this problem. There are just various trade-offs between how fast the robot goes and how close it gets to the walls. Okay, again, this is a very old experiment, so I apologize for the low-res graphics here. Here's, I think this is our first fitness curve visualization. We have evolutionary time measured in generations on the horizontal axis here, and we have phi or fitness on the vertical axis here. Theoretically, phi is multiplying together 3 terms, and each of these 3 terms can range between 0 and 1. So the theoretically maximum value of phi is 1. That's the theoretically optimal behavior. You'll notice that this evolutionary algorithm after 100 generations is only at a phi of 0.2, but it's made evolutionary progress over that period. Yeah? Okay, no physics engine here, so the researchers are taking every set of synaptic weights that the genetic algorithm is considering, they drop it in the robot, they let the robot to run around in the maze for a few seconds. When it's done, they compute phi, or the computer that's attached to the robot computes phi. They drop the next set of synaptic weights into the robot. They put it back at the beginning of the maze, run it again and again and again and again. And for however many sets of synaptic weights they have in the initial random population, it takes them 40 minutes to do that. So every generation takes 40 minutes to execute. They ran this experiment for 100 generations, which took them a little under 3 days to do. Hopefully they didn't do it all in one sitting. Takes a while. Okay. Here's what they got at the end of the 100 generations at the end of 3 days. Each line segment here, the center of the line segment indicates where the robot is, and the angle of that line segment indicates the orientation of the robot in the maze. How's the robot doing? Clearly not optimal. How's it doing? Would have been nice to see an MP4 of this robot, but we weren't quite there yet in 1996. What's the robot doing?
If I'm not mistaken, it looks like he made it.
Certainly made it, yes, absolutely. It drives around the maze. It did it. If that was the desideratum, get around the maze, yeah, not bad.
It looks like it pretty much goes straight, and then when it gets close to a wall, it like pretty much stops and then like turns on one wheel and then goes straight, like sort of.
Absolutely. So, okay. We didn't say anything about exactly how to solve the problem. If you look at it, it tends to make you frustrated after a while. It could be a little bit better, and maybe if the researchers had just kept evolving neural networks, they would have got there. But not bad, not bad. Okay. What's plotted down here is, again, on the horizontal axis, evolutionary time, the 100 generations. There are, I'm sorry, it's hard to see, there are 3 curves in this figure. The 3 curves correspond to the 3 fitness components. Uppercase V, the solid line, is the total amount of rotational velocity of the wheels. The dotted line that you see here, this is trying to equalize the rotational velocity of the wheels, get the wheels to do the same thing as much as possible. And the dashed line is how close the robot is getting to the walls. What can you tell me about what evolution is doing with these 3 terms over evolutionary time, over these 100 generations? Let's start with the solid line, the total spinning of the wheels. How does that change over evolutionary time? What was happening in generation 0, right at the beginning with random controllers? What were the wheels doing in response to randomly weighted neural networks? Moving kind of slowly, right? So very little turning of the wheels, and over about 50 generations, the neural networks evolved to spin the wheels quickly, either quickly forward or quickly backwards. And then in the remaining 50 generations, the wheels don't spin any faster. What about the dotted line shown here? What's happening? It's jumping around quite a bit and then settles to a relatively low value. What does that mean? What does that mean that 1 minus the square root of delta v, delta meaning the difference between the velocities of the wheels, what's happening? Yep.
Trying to go more straight, basically.
It's trying to go more straight. It's trying to minimize delta v, but 1 minus delta v, forget the square root from, 1 minus delta v is actually lower later in evolution than it was back here. What's happening? What does that mean?
To put it sort of colloquially, the evolutionary algorithm is learning to care less about the wheels staying at about the same velocity than that the overall movement of the robot is faster without collisions.
Absolutely. So evolution is caring less. It's trying to make all three of these fitness terms be as high as possible, but it's having a hard time with this one, or it's kind of giving up on it a little bit. It's easier to get the robot to go forward and stay away from the walls if it cares a little bit less about maintaining the same radial velocity of the wheels. So it's a little confusing because this particular controller causes the robot to go straight, but most of the controllers in the population are actually causing the robot to swerve a bit. Delta V is never quite brought down to 0. So as I mentioned, evolution is trying to optimize multiple competing desiderata. We want a bunch of things to be happening here. We actually want 3 things to be happening here, and it's kind of fumbling one of the 3. Evolution can't reconcile all 3. It cannot find a way to get all 3 to be close to 1.
For this specific maze, is there, I think this is a 2-part question, is there an end goal for it, or is it just like make your way around the maze without hitting edges?
Great question. The answer always comes back to the fitness function, right? So if the fitness function is 1, if there is some set of synaptic weights that when you drop it in the robot generates a phi of 1, what behavior is it? It's a behavior that makes V high, makes this thing high, and makes this thing high. And then you got to work backwards from that to what the actual V's and I's would be that would cause that to happen. And it could be just get around the maze once. It could be drive in a tight spiral through the maze backwards 3 times. It's not really specified here. I haven't really given you the units of rotational velocity or the actual values of I. So it's kind of hard to figure out exactly.
So with an angle, you'll have to have another sort of variable that somehow says like the closer you get to here, then.
Could be, yeah, absolutely. We could put some particular object in the maze that it's supposed to go towards that would produce some particular pattern on the proximity sensors if they're close, for example, right? Some object that the robot could see with its proximity sensors, and then we could throw a term into the fitness function that would select for that pattern to emerge, for example. Yeah. Okay. I'm going to skip this. This is the researchers' attempt to show how evolution was juggling these 3 fitness terms over evolutionary time. Let's have a look at up here. This is one evolved individual set of synaptic weights, one individual neural network. They just wanted to kind of see what the robot would do armed with this evolved brain. They took the vehicle, set it at this position, and pointed it into this corner, and the robot drove forward and then turned around and started driving through the maze. Perfect. That's exactly what you would like the robot to do. For fun, the researchers set these synaptic weights. I'm sorry, I misspoke earlier. I said that the genetic algorithm set these line thicknesses. They didn't. The human researchers, by hand, tuned these synaptic weights, so set these synaptic weights to produce the Bratenberg coward. If there's high proximity on your right, turn to the left. If there's high proximity on your left, turn to the right. They built that in. They built a Bratenberg vehicle, which they thought was optimal. Dropped that into the robot, put the robot at this position, and faced the robot back into the corner. And what happened? What did the line segments tell you about the behavior of the Bratenberg vehicle in this physical body? What does it do? Absolutely, right? So it goes forward. Neither proximity values are firing very strongly, but now they start to fire more strongly, and one is just going to fire a little bit stronger than the other, so the robot's going to turn, and now the other proximity sensor is firing, and so now it's afraid, it's the coward, it turns away, ping-pongs back and forth, and becomes paralyzed with terror, and comes to a stop and just wobbles back and forth forever. The Bradenberg vehicle, or a bilaterally symmetric, bilateral meaning the left side is the same as the right side and vice versa, a bilaterally symmetric set of synaptic weights is non-optimal. It's actually not the right thing to do. When they cracked this evolved controller open and looked at all the synaptic weights, it was not symmetric. There was some weird patterning of synaptic weights, and it was not bilaterally symmetric. Kind of interesting. Obviously, bilateral symmetry is optimal. Look at us. We're fantastic. We survive in this world, more or less. It's obvious that's the answer. Yeah? Here's one piece of evidence, and we'll see many more as we go, that there are other solutions out there. This robot drives very nicely through the maze, but it's got a non-symmetric brain, or at least a non-symmetric set of synaptic weights. Kind of interesting. Okay. One last observation we'll make about this robot before we move on. They knew that the top speed of the robot was 80 millimeters per second. The wheels, when they were spinning at plus 0.5 and plus 0.5, the robot would go 80 millimeters per second. That's how fast it could go. But the evolved controllers only ever drove the robot at a maximum speed of 48 millimeters per second. Why? There's all this lost opportunity. Evolution could have evolved the robot to go faster. Why not? Why didn't evolution evolve the ability for the neural network to drive the robot at top speed?
Physics would enforce things like momentum and friction on the robot, so if it goes too fast, it starts to lose control with things like turning.
Yeah, it could very well be, but at this small scale that we're talking about, this robot has a very lightweight, the wheels, friction, it's okay. It can drive, if someone practices, and these researchers did, they can remote control drive this robot at 80 millimeters per second around the maze. It's a good observation. It would be true if we were talking about actual autonomous vehicles. 80 miles per hour, not such a good idea. That's not the reason. Why?
I think so that it gives it a little bit more control. So then if it's going towards a wall, then it can bump up the speed of the wheel that will turn it away, and it will actually keep its speed up throughout the whole thing. Rather than have to like slow down one wheel to pivot, it can just like keep speeding through the maze.
It could be that it gives it enough time to turn. We're getting closer to the answer. The researchers, again, when they're driving it, the ones that are practiced at doing this, they can drive it at 80 millimeters per second and keep it at 80 mm per s while taking a turn.
It doesn't know its surrounding, right?
Sorry?
It doesn't know its surrounding, so it's sort of just...
It doesn't know its surroundings. Good, okay, now we're getting closer. It knows something about its surroundings. It's got 8 numbers every 10th of a second. The researchers, the trained drivers, they've got a lot more than 8 numbers, and they're getting that increased amount of information at a faster rate than a 10th of a second. This would be like driving, where you squint your eyes so you can't see very much, and you keep your eyes closed, you're blinking at a regular rate. Again, don't try this. But if you did, you'd find that the only way you can drive safely doing that is to go slower. Evolution has found that 48 millimeters per second, more or less, is the top speed that it can drive the robot, given the limited frame rate, or the cognitive frame rate, of the robot. This is just a fancy word for sort of the rate at which the robot can think and process information coming in from the world and do the right thing. It's got a limited cognitive frame rate. That's the speed it can go. If we were to take this robot today and instrument it with 2025 sensors that have a refresh rate of a nanosecond and ran everything else exactly the same, I'd bet you $100 Evolution finds a faster speed to drive the robot through the maze than 48. Yeah. Again, the reason we're making this observation is there's usually no such thing as optimal behavior. There's always a trade-off between the things we want it to do well. And there are also limitations and opportunities placed on behavior by the specific physiology of the machine or the organism. Okay. Any questions about the Italian approach before we switch to the English approach? Okay. Meanwhile, at this time, on the other side of the channel, the Gantry robot was being built in about 1994. There was a BBC episode at the beginning of the semester that I sent you. The BBC reporter went back to Sussex and talked to the Sussex researchers about this Gantry robot, which still exists in the lab back there. Okay, what is the Gantry robot? Like this setup here, the researchers were dealing with mid-90s technology, and they were trying to find a way to evolve a bunch of neural network controllers on a robot. Very similar approach, but they came up with a very, very different solution. This part's the same. They've got a desktop that's going to run the evolutionary algorithm and is going to send synaptic weights down to the robot here. It's going to get values back and compute the fitness of that particular controller when it's controlling this robot. What is this robot? It's called the Gantry robot because, not surprisingly, it's a gantry that is sitting on top of a table in which they've cut out the top of the table and just left the four sides. There is an X trolley. There is a little trolley here that drives back and forth horizontally across the top of this hollowed out table. And then there is a smaller Y trolley sitting on top that drives vertically up and down the length of the X trolley as the X trolley is moving side to side along the table. You with me so far? So we're going to see a lot of crazy robots in this class. This one is one of the crazier ones. Okay, gets more interesting. The tether of the robot is holding a camera that is hanging upside down. So again, I apologize for the poor quality of these old images. This is the camera here, and it's pointed downward. So it would be looking at whatever cool things they place on the floor under the table. But it can't because the downward facing camera is facing a diagonally facing dental mirror. This little circle here is a circular mirror, and that circular mirror is just constantly turning all the time around and around and around. It's not controlled by the neural network, it's just fixed. Why the heck would they do that? Why point a camera down and then put a diagonally aligned dental mirror rotating underneath the camera? They are going to navigate through things underneath the table, but why set up the robot in this way? The robot is the trolley. The robot is both trolleys and the downward pointing camera. So I'll invite you to step into the shoes of all the robots as we go. This one's a little bit harder than most to see through its eyes. What is it seeing?
I'm still a little confused, but is it allowing it to see more of its environment?
Yes, more of its environment. How so?
Because the mirror is shifting, so it's going to be able to see a little bit like the side instead of straight down.
It's going to see the sides of things underneath. and it's going to see with a 360-degree view because this diagonal mirror is rotating all the time, and the downward pointing camera is looking at the glass of the mirror. This thing is a inverted periscope. You know, the submarine sends up the camera and then the person turns the viewer above. That's exactly what's going on here. It's just upside down. So we've got a robot that's moving around the table up top, and this camera is following and navigating around and looking around underneath the robot. Why would they build a robot in this way? Certainly not a Bratenberg vehicle. Doesn't look anything like Spot the robot dog, or a humanoid. Why did they build it in this way? They're going to start, or the desktop computer is going to start downloading sets of synaptic weights onto little circuits in the two trolleys, and getting camera images back, and then computing the fitness. How well does this robot do at navigating under the table? We haven't said what the fitness function is. We don't know what it's supposed to do, but you can assume that at the beginning, when we download a random set of synaptic weights, the robot's going to crash into things and probably not do a very good job of what we want it to do. Crash, 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 crash. Keep sending controllers, and after hundreds or thousands of controllers downloaded onto this Gantry robot, it's hopefully going to start evolving to do a better job at whatever it is we want it to do. Why did they build the robot in this way? To facilitate this trial and error evolutionary process. Think about our poor Italian researchers that are on the other side of the English Channel that had to sit there for 3 days and do what?
Well, this just can automatically reset itself.
This thing can automatically reset itself. So they wrote a little script that's about 8 lines of code that when a controller is done, that little piece of code resets the 2 trolleys and the camera back to the initial position. These researchers are also going to run this Gantry robot for days and weeks, but they don't have to babysit it. They can't leave it for the whole time, but there's less babysitting going on. They're automating the process. That's why it's built in this crazy way. Okay, so we've got back and forth on the X trolley, back and forth on the Y trolley, and the tilted mirror can be rotated. 2 lectures back, we talked about mechanical degrees of freedom, the number of ways in which a machine can move. Here's 1 mechanical degree of freedom. Here's about 2.5. So 1 plus 2.5, 3.5 degrees of freedom, 4 degrees of freedom, 5 degrees of freedom. You can count them up. In the Gantry robot, there's 3 degrees of freedom. The X trolley, up and down, back and forth. The Y trolley, forward and back. That's the 2nd degree of freedom. The 3rd degree of freedom is the rotation, the constant rotation of the tilted mirror. The controller of the robot is going to control, or the controllers are going to control the first 2 degrees of freedom, the 2 trolleys. The 3rd one is the neural network can't control the dental mirror. That's just going to spin on its own. So we've got 2 mechanical degrees of freedom we want to evolve control over. So you can think of it as 2 motors, one that controls the X trolley, one that controls the Y trolley, and this robot has 7 ways to sense. This is a little weird, and this was their way of getting over some of the limitations of 90s hardware. Okay. Underneath the dental mirror, they just put a plastic disc, a bigger plastic disc like you see here. And as this thing is running around underneath the table, it can bump into things with this plastic disc. And there's a little sensor sitting in here that can deflect detect the deflection when this thing hits something. They take that information and boil it down into 4 binary values. At the current time step, has the robot been bumped from front right, back left, and or front left? So we have now four binary sensors. 0, it wasn't bumped in that direction. 1, it was bumped in that direction. Okay, now let's tackle the camera. There was no neural network on Earth in 1994 that could take in a video feed and compress it down into usable information. That had not been solved yet. So the researchers built in a little bit of feature engineering. They're going to try and pull out some features from the camera that they think are going to be useful to the neural network in controlling the robot to do whatever we want it to do. How did they do this? They take the raw CCD image, the raw image from the camera. So we've got north, west, east, and south. Remember that we've got this rotating dental mirror. So that rotating mirror is giving a 360-degree view around the camera. Imagine this is a square view of all around the robot. They're then going to compress it a little bit into this circular pattern. We don't need to worry about why. At this point, we're still kind of dealing with raw pixel values from 360 degrees around the periscope. And they're then going to drop 3 circles of arbitrary size and arbitrary position into the field of raw pixels. They're going to take the colors of all the pixels inside each of the circles and scale them to grayscale, and then further compress them again into a value between 0 and 15. 0 is all the pixels inside the circle are black. 15 is all the pixels inside the circle or white. So these 3 circles are basically picking up the average amount of brightness at 3 different places inside the raw video feed coming back from the camera. Again, seems like a weird, arbitrary thing to do. Let me give you an analogy. At the moment, from your perspective, it seems like everything here at the front of the room is a movie, that you can see everything. You can't. You can see either my eyes or my lips in good detail. Everything else is incredibly blurred out. But then you move your eyes to the screen, down to the desk in front of you, back to me. You're bouncing around, and at any one point in time, you're only seeing a resolved picture of about this size in front of you. That's foveal vision. You've got a fovea at the back of your eye, foveal vision, fovea at the back of your eye that can resolve a very small piece of your overall visual field. The researchers were inspired by that, and they're trying to pick out bits of the visual field, of the robot's visual field, that they think is going to be useful to the robot. Instead of just one, they kind of arbitrarily said, let's allow the robot to have 3 different fovea. There are other species on Earth that also have multiple fovea. We are not one of them. You can only focus on one small bit of your visual field at any one time. Okay. How they determined the size and position of these circles, I'll explain that in a moment. But let's go back to seeing the world through the robot's point of view. The robot has 4 binary sensors so far that can be either 0 or 1, and then a 5th, 6th, 7th sensor, which corresponds to the 3 receptive fields or the 3 fovea. Those 5th, 6th, and 7th sensors can report values between 0 and 15. Okay, so at this point, we now have a robot that at any point in time is receiving 7 values, 7 incoming sensory values. 3 of them are visual values. 4 of them are proprioceptive sensors. Is it bumping into something? Those 7 sensors are going to propagate their values through a neural network, through a set of synaptic weights. And those values are going to arrive at 2 motor neurons, One motor neuron is going to drive the X trolley back and forth, and the second motor neuron is going to drive the Y trolley up and down on top of the X trolley. That's the brain of the Gantry robot. We'll talk about what it was evolved to do on Thursday. You have a quiz due tonight, and you're working on A5, 9, or 10. See you then.